Welcome to this lecture from our thermal building physics course, where we are talking about multidimensional heat conduction problems. And this lecture will be about the analytical theory on that. We will quite soon limit ourselves to 2 dimensions when we talk about multi-dimensions. But when we are general, we have 3 dimensions, so we have to use the thermal gradient of the temperature gradient in all 3 directions, and then we can, in a general heat conduction equation, we can evolve how things develop with time. So that's a general heat conduction equation. But for this lecture, we look upon it a little bit more simply. First simplification is that if the thermal properties of a material are constant, we can write the formula a little bit simpler. And that is normally for building applications the case, that it's a good approximation. Next is that we limit ourselves to 2 dimensions, and we take only the steady states or constant conditions, so everything that is time dependent will vanish. And this we have then is the Laplace equation, and we're going to look to solutions to that. So we are going to solve it for a 2-dimensional field. So we take such a piece of material with width A and height B, and we're going to look to solutions which might at first be looking a little bit special, because we assume that we have 0 degrees temperature on 3 of the surfaces, except only the top one, where the temperature is some function that varies with where we are along the x-axis. So let's try to see if it's possible to make solutions in that case. We use the temperature theta, which is a parallel temperature to the real temperature as such. So we have a shift in the temperature by the level T0. So we make an assumption, and this is not something I invented. I have to take it from some textbooks, so I'm really conveying that information because it's a little bit fantastic. We assume that the temperature we're looking for at any point, x and y, in the domain where we are going to calculate it, can be taken to be a product of a function capital X, which depends only on x, multiplied with another function capital Y that depends only on the coordinate y. And that's just the assumption, so let's go forward with what the clever people from textbooks have written. I'm not going to go through all the mathematical derivations. You can read it here. If you stop the video, you can read the slide more slowly. But I'll just end up to say that after these derivations, we have something which are some partial differential equations. One thing that depends only on x is equal to something that depends only on y. And since x and y are mutually independent, well, then the solution to this could be more or less only if the 2 things are equal to one another, being equal to a constant. And here we continue assuming that this constant is a positive constant. We take the value zeta squared, then it will be positive. And in that case, those differential equations, they can be written here separately for x and for y as such. And they are quite well-known ordinary differential equations. They have each of them these 2 solutions here. So here are our solutions to what should it be for the x and the y function as we continue. Now, so the solution should be the product of the x function and the y function. So this is how we can write it, inserting the solutions for those functions. But this is, as very often when we solve differential equations, we have some constants that we must find, and they can be found in a specific case based on the boundary conditions. So that's what we're going to do next. Here we have the solution again, and our case that we're talking about. And we see the 4 boundaries. So let's see if we can use that information to help us to define what should be those constants C1, 2, 3, and 4. And here are the solutions. I'll not go through all of it, but just take one example. For instance, the bottom here, where theta should be 0. X can be any number between 0 and a, and y is 0. So if we insert that up here, inserting 0 here for y means that the exponential would be 1 here and there. So it says C3 plus C4. And whatever is over here, we cannot decide because it depends on x. And we cannot control what that would be in that range. So a solution to make sure that theta will be 0 would be to say that C4 and C3 must be equal to each other with a minus in front of them. And then we can continue to develop it a bit more for the other 2 or 3 boundary conditions. And ending up to say the fourth one, then we have this function of the temperature that could be anything that we would like to insert for that function. I'll just continue working a little bit more on the third boundary condition because from the previous slide, it said something where we should have insert some roots for this zeta where it could be equal to n, any number, 1, 2, 3, 4, and so forth, times pi and divided by the thermal diffusivity A. Sorry, the width A, I should say. So n can be any number. So we can have one solution or another solution. We can have a multiple set of solutions. And any solution and in addition to with another solution will also be a solution because the Laplace equation is linear, so we can add solutions together. So that means that if we take the solution from before and insert this value for zeta, well, then this will be our equation here. And what we have in the bracket here, those exponentials, is here translated to the hyperbolic sine function. And you may recall the definition of the hyperbolic sine function, where you can recognize some things from up here, except the factor 1/2 or division by 2 here, which is the only difference between when here we have all the things that were in the constant an. The difference between an star and an is simply that number 2, just for explanations. So that means that we have something that we can go forward and solve, except that we have not talked so much about the fourth boundary condition. But to find something that very easily fits in the solution that we have, well then if we have something where the temperature along the top boundary, if it varies as a sine function with the x value, well then we have something that very easily fits to become a solution. And I'll just draw it over here, if the camera can follow me over here. If that is our calculation domain, well then if we have such a sine function for the temperature on the top, the topping here, that would be the top temperature, and that should illustrate a sine function as well as I could draw it. That would be a solution that very easily fits into this thing here. And then we should insert, for A1, we should insert this theta top divided by the hyperbolic sine function as we saw from the equation on the slide just before. And all other coefficients should be 0. But that's because we drew such a sine function here. What we might also do, and what could also be a solution, when we should then involve some of the other coefficients, A2, A3, and so forth, could be to have another sine function with another frequency, like this. This could also be a solution. And we could also have one which has yet another frequency. If I can draw it, it's not so easily, but let's see, and so forth. And we can have even more, and some of them we can have varying amplitudes and also directions. So perhaps the next one will go like this. And now it becomes a mess because my drawing is not so perfect. But just you can have any sequences of frequencies and amplitudes, and each one of them will fit with different coefficients in our solution, and any linear combination of those. So that means that all such, although it looks like a mess, can possibly also be used as a solution. So on my next slide, I have, here's just to illustrate how we can insert for the different coefficients with the different variations of the sine function. But that means that we have, what I'm just explaining here is that we have in that case with the sine function, actually the first one I was drawing. In that case, we have the formula that expresses in any point x comma y within our calculation domain what is the temperature at that point. But what I was going to say is that in the case that we have this multitude of sine functions, well, then we can also have those as solutions. What I'm drawing here is to say that if we use Fourier analysis tells us that any function I might have up here, I'm just drawing something arbitrarily. If I want to have this to be my top temperature, if it looks nice, I don't know, but that can be, according to Fourier analysis, be made as some combination. Clever mathematicians has to find out how to find them, but some combinations of sine functions with varying amplitudes and frequencies. So that was one choice of a blue function. Another interesting blue function that I might very often be interested in, and now let's see if I can somehow delete the blue. That's not easy, of course. But here I did my best. I hope you can imagine still we have some of all those sine functions. But one function that's interesting us a lot could be if we have a constant top temperature here, up here. And even such a function can also be described as a combination of sine functions as such, according to Fourier analysis. And then it becomes interesting. And that we can, in principle, insert in this formula using the Fourier analysis. The solution becomes, in that case, with the constant top temperature, becomes this function here. Well, it's a function, I don't know if your fingers look nice, but I put it in a red frame because it's something, if we are careful, then we can rather easily use this function. So to insert a coordinate x and y, then we can find the temperatures according to all the other, according to the top temperature also. So in this more interesting case, we have solutions. So is this good for something? Yeah, well, let's see. Actually, we can use this principle of superposition because we had this special condition that we're working with the top temperature. But in general, we would like to have also possibilities to calculate other cases. So how would that look then if we do that? So for more complex problems, we can use a superposition. And I have here with me on the slide an example, which I will also elaborate a little bit more on the whiteboard here. But just here on the slide, show a little bit more. We have in real temperatures, T temperatures, we have 100 on top, 50 on the right, 50 on the left, 20 on the right, and 20 on the bottom. So what we do then, well, we're interested to find, for instance, the temperature in such a point here. And how can we do that based on the theory I've presented to you so far? Well, we kind of make a shift, we figured out. So first of all, we replace the temperature T with a theta temperature. And also, we separate the problem into two problems with the postulate that we can have as a multiplication of solutions from one to solutions from the other. Well, then we have the total solution for the problem we have at case. Again, my point is now in both of the two solutions. So the red point I'm interested in looks here. And here's how I calculate between T temperature and theta temperature just by shifting with a temperature of 20. So that becomes my solution, but how then can we work with it still? It doesn't appear so clearly, does it? Now I go to the whiteboard over here. I have to erase a little bit here because I want to reuse some of the things I had. So I'll just write, that's because I don't have so much space, so I'll just write here the temperatures that we had. We had T equal to 100, T equal to 50, T equal to 20, and T equal to 20 on those borders. That can be equated with, in terms of theta temperatures, what I have over here. But I have to work, I have only solutions in the case where the top temperature is different from 0. I have 0 on the left, right, and bottom borders. But I can work on having one solution and adding it to another. So, first of all, the theta temperatures have to be changed from T temperatures. So we use the reference temperature 20 as the difference between them. So first of all, I will somehow work with a solution where the top temperature is 30. That is 50 minus 20. Then I took care of the left-hand temperature, but yes, I wrote it wrongly, did I? Yeah, on the top. And then I add something more, which is what is the influence from the top. And that is 100 minus 20, so that means I have on the top 80 up here. Now what happens to the point? I was interested in this point here. Somewhere here it was located. And when I made when I put the 50 minus 20, I put it on the top, I made a turn of my material. So that means that this point has now been turned and is actually located over here. And then this one, still I'm working with the temperature on the top. That became 100 minus 20, the 80 I have over here. So now the point I'm looking to is still this point here. So if with my formula I showed on some of the previous slides, I can find this temperature in theta units and add to that the temperature over here, then I have my solution for the temperature, and I can translate it back to T temperatures by adding 20 if you're interested. I hope that all that makes sense. That completes at least this lecture here, and I hope you enjoyed it. Snip, snap, snoodle. That's all, folks. So I hope you can use it.